In order to describe the shape of the sampling distribution of p hat, or the proportion, we also have a central limit theorem that we can apply if appropriate. This is not the same central limit theorem that we used for means. So theorem 8.4, which is the central limit theorem for proportions, states that if a random sample of size n is selected from a population with a population proportion p, then the sampling distribution of the proportion can be approximated by a normal distribution whenever the sample size is sufficiently large. So very similar to the central limit theorem for the mean x bar, except our criteria that we're considering to be large is a little bit different. For proportions, a sample size n can be considered sufficiently large whenever both n times p is greater than 10 and n times 1 minus p is greater than 10, where remember, n is the sample size, p is the population proportion. So if both of these criteria are satisfied, we can use an approximately normal distribution to describe the shape of p hat of the sample proportion. So if sample size n is sufficiently large, meaning that n times p is greater than 10 and n times 1 minus p is greater than 10, then the sampling distribution of the proportion can be approximated by a normal distribution. And we know that its mean mu sub p hat is equal to p. And the standard error of the proportion we know is equal to sigma sub p hat, which is the square root of p times 1 minus p divided by n. So let's look at example 17. It says, according to a study conducted in one city, 39% of the adults in the city have credit card debt of more than $2,000. A simple random sample of n equals 100 adults is obtained from the city. Describe the sampling distribution of the sample proportion of adults who have credit card debts of more than $2,000. So this is similar to one or a couple. I think we did 3 examples like this when we were looking at sample means, where I said describe the sampling distribution of the mean x bar. Well, now we're doing the same thing, except we're describing the sampling distribution of p hat, because that's my variable of interest. Before we do that, let's look at the first 2 sentences and write down what we know. So we're looking at our population is adults in a particular city, and we're measuring the proportion of them that have a credit card debt of more than $2,000. So this 39% represents the population proportion of adults in the city that have credit card debts of more than $2,000. So this is P. So P is equal to 39%. Or 0.39. Now, suppose we take a sample of 100 adults from this same population. Let's describe the sampling distribution of p hat, which would be the sample proportion of adults that have a credit card debt of more than 2,000. So imagine if we took all possible samples of size n equals 100 from this population of adults, and we measured the proportion of them that had a credit card debt of more than $2,000. That's what p hat is. So we'd have all these different p hats from all the different samples of size 100 that are possible. So I want to describe the sampling distribution of p hat. So remember, when I say describe the sampling distribution, I want 3 things. I want the shape. So in this case, I want the shape of p hat. How is p hat distributed? I want the mean of all the p hats. And I want the standard error of all the sample proportions, or all the p hats. So let's start with shape. So let's go back, remind ourselves of this new central limit theorem for proportions that I introduced. So we can only apply the central limit theorem if n times p is greater than 10 and n times 1 minus p is greater than 10. So let's check. So is n times p greater than 10? And is n times 1 minus p greater than 10? If so, we could say that p hat's approximately normal. So let's check. So n times p is going to be 100 times p, which is 0.39. And that's equal to 39. And that's bigger than 10, right? 39 is bigger than 10, so that checks out. And then we have to multiply n times 1 minus p. So 100 times 1 minus p, or 1 minus 0.39. And that's equal to 100 times 0.61, which is equal to 61. And that's also bigger than 10 or greater than 10. So since both of these criteria check out, we can say that p hat is approximately normal. So we were able to apply the central limit theorem for proportions. So the shape of p hat is approximately normal. The mean of all the p hats is equal to p, which was stated that it's 0.39. And now we could calculate the standard error, right? So we could take the square root of p times 1 minus p divided by n. And if we plug that in, we're going to get 0.39 times 1 minus 0.39 over n, which is 100. So let's plug that into the calculator. So you plug in, I'm going to do it on my calculator. Then I got about 0.0488 for the standard error. So that is how we would describe the sampling distribution of p hat in this case. Approximately normal with a mean of 0.39 and a standard error of 0.0488. So now let's look at example 18. So example 18 says a large city claims that 60% of its residents support a new public transportation initiative. To verify this claim, a random sample of 200 residents is selected. What is the probability that the sample proportion of residents who support this initiative is between 55% and 65%? So this is a little bit different than the previous one that we did, but it's still referencing the same statistic or the same variable, which is the sample proportion p hat. Except now I'm asking you to calculate a probability regarding the sample proportion. But before we even get to the question, remember what I always tell you guys to do. Summarize and pick out the important pieces of information, right? Identify the population, what could we use to describe the population, and so on and so forth. So we're looking at the residents of this large city. That's our population. And we're being told that 60% of them support this new public transportation initiative. This 60% is a proportion of the population, right? It's the ratio or the part of the whole that says we support this initiative. So 60% out of 100% are in support. So that value is P, the population proportion. So this is the population proportion of residents that support the initiative. So that's what P stands for in words. And P is equal to 60% or 0.60. So now what we're going to do is we're going to sample from this population. So I see, okay, we're sampling. So N is equal to 200. So we're going to take 200 residents. And now we're curious as to what is the probability that the sample proportion of residents who support the initiative is between 55% and 65%. So remember, anytime we answer a probability word problem like this, I always have you guys write it in, you take the English representation, right? Take the sentence and let's translate it to mathematical notation. So we're being asked to find the probability that the sample proportion is p hat, right? So the proportion of residents from my sample of 200, so find the probability that that p hat is between 55% and 65%. So I want to know what's the probability. I'm going to just move p hat over because we want to know what's the probability that p hat is between 55% and 65%. Now, typically, we write proportions as decimals. So I'm just going to rewrite this as what's the probability that p hat is between 0.55 and 0.65. So in order to answer this question, I need to know about p hat, right? My random variable is p hat, the sample proportion of residents that support this initiative. I need to know its shape, what's the mean of all the p hats, and what's the standard deviation of all the p hats, right? When we were working with X or X bar, we were doing the same thing. We needed to know the shape, the mean, and the standard deviation. It's no different with p hat. P hat's just my random variable. So remember your central limit theorem for proportions. We want to check that n times p is greater than 10 and that n times 1 minus p is greater than 10. So let's see. N times p is going to be 200 times 0.60, which is going to be 120, which is greater than 10. And now let's check that 200 times 1 minus 0.60 is also greater than 10. And 200 times 1 minus 0.60 is going to be 80, which is also greater than 10. So since both these criteria for the central limit theorem for proportions checks out, we can say that p hat is approximately normal. So now I feel comfortable drawing my normal distribution. Now this normal distribution represents all the sample proportions of residents who support this initiative. So in the center is going to go the mean of all the p hats. And the mean of all the p hats, or mu sub p hat, is always equal to p, which in this case is 0.60. So the mean of this distribution is 0.60. And we could also calculate the standard deviation, right? So we're going to calculate sigma sub p hat, which is the square root of p times 1 minus p divided by n. So I'm going to have the square root of 0.60 times 1 minus 0.60 over n, and n is 200. So I want you guys to plug that into the calculator. Calculate the standard error. I'm doing the same as well. And to 4 places, we get about 0.0346. So now that I know the shape of p hat, it's approximately normal, the mean is 0.60, and the standard error is about 0.0346, I can answer this probability question. So Where in this normal curve is p hat between 0.55 and 0.65, right? This is what we're trying to solve for right now, what I just highlighted. Well, 0.55 is less than 0.60, right? So let's put p hat equals 0.55 to the left, and 0.65 is to the right. So let's put a p hat of 0.65 to the right of the mean. And we want to find the proportion of area between the two, right? And this proportion of area is going to represent the probability. And although we're working with a different random variable now, right, p hat, which I introduced in these last couple of lectures, it follows a normal distribution. So we can still use the normal CDF function on the calculator to find this proportion of area under the curve. As long as the random variable is normal, we could use normal CDF. So my lower bound on the shaded area is going to be 0.55. The upper bound is going to be 0.65. The mean is 0.60. And the standard error is 0.0346. So let's go to our normal CDF function in the calculator. My lower bound is 0.55. My upper bound is 0.65. The mean is 0.60. And the standard error, the standard deviation, is 0.0346. We could paste and enter, and we get about 0.8516. So that's the probability, that 0.8516, that the sample proportion of residents who support the initiative is going to be between 55% and 65% if I were to take a random sample of 200 residents. So we're going to do another application question in the next video. So we're going to keep practicing this.